So hi everyone again. Hi, hello and welcome to another Saturday live stream, Saturday microscopy live stream. Microbehunter here again. And I want to say a big hello all around the world again. I hope that everything, the sound works fine as always. I've seen that many people already started to join the chat and started to comment. Yeah, and that's a very nice thing. And what I would like to do today is I want to do several different things. I want to talk a little bit about making measurements under the microscope. So I'm going to explain a few things a little bit in theory. And then later on, I would like to look at a few slides that I prepared last week. And then I'm going to also, of course, like every week, I would like to answer some questions. Okay, sound is okay. I'm just hearing, and I would like to also make a quick organizational announcement. Today in the evening, so after a few hours, here in Central Europe and also in other countries of the world, summertime will start. And this means that I have to change my clock by 1 hour. And this could mean that maybe next week, for some of you around the world, maybe the time will be 1 hour off from what's been up to this point. So I just would like to inform you on that so that you're not surprised that maybe in some countries around the world, if you do not change your clock tonight, that there might be 1 hour, different. Okay, just that you know. Because I will always pre-announce the videos anyway. There's this countdown timer, and it will actually say how many hours it will still until the start of the live stream. So I just want to make you aware of this possibility. Okay, it will be 1 hour late. Well, the thing is today in Central Europe in a few hours I have to change the clock 1 hour forward. Okay, now I don't know how this actually influences now the time in other countries around the world, because in some countries you might also switch the time, in some countries maybe not. So I recommend that you simply kind of check the video a few hours in advance, because there's this timer, this countdown timer. Okay, so what I'm going to, a second announcement is I'm going to do today's live stream a little bit different than the live streams in the previous weeks. We're going to see how this works. I'm going to I'm going to address your questions later on. Okay. So what I'm going to do is maybe for about 30 minutes or 20 minutes, I don't know. I will not be responding to any questions. But please do ask questions, okay? And then later on, I will go, when I'm finished with all of the input, then I will go through the chat and I will try to answer pretty much all of the questions, okay? So I would like to keep this separated a little bit today. I'm going to try it like that because some people might be more interested in the theory input. Some people might be more interested in the question and answer session. So I'm going to try to keep it a little bit separate. I don't know if I'm going to keep it like that in the future, okay? I just would like to try it out, and then we're going to see. So my suggestion is that you please still post questions, even if they are off topic. That is fine. I will try to address them later on. Okay, we're going to see how it works. And so what I would like to do is the following. Many of the microscopes, and I'm going to switch now, many of the microscopes will have, look at the arrow, will have a little scale on the stage, okay? Usually there's one for the x-axis and one for the y-axis, okay? So if you rotate, look, these, by the way, this is hair, my hair, okay? And if you move the x or the y-axis, then you're able to see that, this is actually going to move. And the other one you are not able to see because I did not point the camera towards it. But this one is now the x-axis, this one is the y-axis. And today I'm going to show you 3 methods on how you can estimate the size under the microscope. Okay, I'm going to show you 3 methods. One of them will be used with this scale here. I'm also going to use you won't believe it. It is possible to use a ruler as well. I'm going to show you. There is a little bit of math involved. It's not difficult, but yeah. And another third method that I'm going to show you is by using a so-called a special micrometer slide, okay, which you can buy, and there is a scale on it, and I'm going to show you this method as well. Now, I've been thinking long about whether I should do a video like this or not, because it might be a little bit specific, but I think that anyone who's got a microscope, I think it's good if you just have heard about it once, and then you can decide yourself of whether it's useful or not. But I think that many of you might already have a scale like this on the side, and you might not know how to properly use this, okay? So this is something that I would like to show you as well. And what I'm going to do first is I'm going to explain this scale by using a paper model that I made, okay? Because it's easier for me to explain this, okay? So this is basically the model that I will use. So I'm going to show you how you can actually measure sizes and distances and so on. Okay, so what you have is on a microscope stage, on some microscope stages, you have two of those scales, one on the x axis and one on the y axis, and they're basically millimeters. It goes from 0, in this case I stopped at 15, but the slide over here, it goes all the way to 50, 60 even on my microscope. So actually, so there's a long one, right? And these are in millimeters. Okay, just like a regular ruler, right? And then there is a smaller scale which goes from 0 to 10. I actually showed it to you over here already. See, that's the smaller one over here from 0 to 10. And those two scales can be moved against each other, okay? Depending on your stage, either the smaller one moves, okay, or maybe the larger one moves. It really doesn't matter. It's the same thing, okay? So what I would like to do now is I would like to show you how this can be used to measure out distances. Now, there's also another use for this scale, which is not the measuring, but if you have a permanent slide, okay, so one that always stays the same with mounting medium, and the specimen stays the same on the same position all the time. And there is some interesting thing on the slide that you would like to remember, and you would like to write it down, the position, okay? Then you can also use this as to get the coordinates of this specific thing that you're interested in, okay? So what I would like to now show you is how this works and the advantages of this. Notice that one scale here, the large one, has millimeters, and the one that goes from 0 to 10, okay, look at this, where this stops. It's compressed, it's shorter. When this one over here is 9, this one over here is 10. So the distance of the smaller one is also smaller, okay? And you can actually also see it over here. Notice when I'm just going to arrange this here. Notice that the smaller scale, look here, okay, the 10 actually stops. Let me do it like this. It's easier like this here. Notice that this 10 over here, okay, stops 1 millimeter short of the 20 over here. Yeah, so this smaller scale is compressed. It's actually only 9 millimeters long, even though it goes from 0 to 10. The distance is actually a little bit smaller, and that's supposed to be like that. Okay, how does this now work? If you would like to now measure a position, then just forget about this one over here. Just look at the 0 over here, and what you do is let's say that this 0 position is over here, and then you can now estimate. This line here is between 1 and 2. Okay, so I would say it's probably 1.5. You would guesstimate. You're right, because it's right in the middle. Yeah, and if it's a little bit further down here, between 1 and 2, maybe it's 1.6. Maybe it's further down. It's maybe 1.7, 1.8, 1.9, and it's of course 2.0, right? When it's completely aligned, right? Yeah, and when the 0 is over here, further towards the 1, it's probably 1.2 or something like that. But you know what? I'm guessing, right? And that's not good enough because I really want to be precise about the whole thing when I want to make measurements, right? And sometimes it's difficult to see because look at this small scale over here. Okay, simply to see exactly where the line is between the 10 and 11. It's kind of difficult to see, right? So yeah, I don't want to guess, right? So what you do is the following. Let's say that I would like to read off this position over here, and I would guess it's maybe about 1.3, right? Because this line here, the first line with 0 lines at 1.3, but I would like to know exactly. So what I do is I go all the way down, okay? I go all the way down this small scale, and I look for the line, any line that lines up with another line. Okay, do you see this here? This one is not lined up, and here it's lined up, okay? And then you read off the value on the smaller scale, and it's 3. So I know it's 1.3, okay? So it's 1.3 millimeters, okay? And then when I advance the stage a little bit, okay? And then this is, I don't know, 1.6, okay? Because this is where it lines up. Okay, or let's keep on practicing. What about this here? What's this here? Well, it is 3.7 because this is where it lines up. Okay, yeah. So you just look for any pair of lines where it lines up. And over here, I don't know. Let's do it like this here. This one would be 5.8. Yeah. And that's basically how you're able to read off the position. Yeah. And what you do now is if you want to measure something, then you're able to measure, I don't know, this place, and then you move the stage until you have some kind of an arrow or so over here, and then you can calculate the distance. Okay. So this is a very convenient way, and I would like to illustrate this right now, okay, by trying to measure out the diameter of one of my hair, okay. So this is simply something that I'm going to try to do now. Okay, so I'm going to switch over to the scene. I think that the hair is still a little bit too thin here. And what I would like to do is I would like to only move the y-axis. So I have to find a hair which is kind of more horizontal. Maybe I'm going to use this hair over here. Okay, this big hair. This one over here, okay? I'm going to go up with the magnification because I have to turn up the light because it's simply easier this way. I'm gonna go up yet further, okay? And I would like to measure out this the diameter of this hair. And for this reason, I already made, would like to measure out this diameter. I already made a couple of arrows in case simply to remember the position here, okay? And what I'm going to do now is I'm simply going to put an arrow up here, so I'm going to remember this position. And maybe some of your microscopes already have an arrow in the eyepiece that points inwards, okay? And if your microscope does not have an arrow, okay, then what you can do is you can use the edge of the field of view. For example, in this case right now, look at the top here. Yeah, this is where it kind of touches. Where it kind of touches the edge. Right? In my case, it's square, but in your case, it's a circle. And so you can use this as a reference point, right? So what I'm going to do is I'm just going to use the arrows that I made. I'm just going to remember this position here, and I'm going to now have to move over now to the mic to this one over here, and I have to read it off. I have a problem reading it off. This is actually 19 because it's not quite 20 yet. Okay, you see, it's not quite 20 yet. It's 19 point. Where does it line up? Lines up, I don't know, it's almost difficult to see. 19.8. Okay, I think I have a difficulty seeing it. Okay, so this is 19.8. I gotta write this down somewhere. 19.8. Okay, so it's 19.8 millimeters. I've got a little board here. Okay, so 19.8 millimeters. And now I'm going to move the, no, that was wrong. Okay, 19.8, it's the other one. Now I'm going to move it until the other edge of the hair. I'm meeting the other edge of the hair, okay? So I've moved from here to here, and I'm reading it off again. And now it is still 19 point, where does it line up? 19 point, Here this is 6, I think. 5, 6, 19.6. So I've got from 19.8 to 19.6 millimeters. So that means my hair has a diameter of 0.2 millimeters. So 5 hair aligned or put next to each other should give me 1 millimeter, which kind of makes sense. Okay, so the common sense check is correct. Yeah. So from 19.8 to 19.6, I've written this down over here. Okay, look. Yeah. Yeah. So basically, this gives me a difference if you subtract it of 0.2 millimeters. Okay, this is kind of at least the thickness of this specific hair. Okay, it's maybe not quite precise because, you know, there's still a little bit of guesswork to do, but you know what, it's good enough for me because not all hair has the same thickness anyway. Okay, so it's going to be fine. And you know what I'm going to do now is I would like to increase the magnification. And I'm going to try the same thing with a higher magnification, and I should actually get the same result. So let's try this, okay? So this is now the 200 times objective, okay? And now I'm going to switch over to the 400 times objective. Oh, look at this, the light is too dark. Okay, so let's move it down here. Okay, and let's focus a little bit. Here again, okay, and let's remember this here, and this one over here is now, let's have a look at here again. This one is still 19, it's not quite 20, it's 19 point, where does it line up? 19.9, if you look here, the 19.9 seems to line up, so I'm going to remember 19.9 millimeters. And let's move the thing over here, the thickness over here until the arrow points to the other one. And now I have, what is this? Also still 19 point, difficult to see, 19.5, 6, 19.7. Of course. Still 0.2, right? 19.9 to 19.7 millimeters. I just realized, maybe, you know what I'm going to do now? Look at this. I'm actually going to increase the size of this here. How is that? I didn't think of that. I think this is so much better. It's a little bit out of focus. I see it's a little bit blurry, so I have to focus this a little bit better. Okay. Yeah. I think this is much better. Okay, so and of course, again, from 19.9 to 19.7, it's still 0.2 millimeters, right? So I would like to simply show this to you, that this is a very easy way of actually kind of estimating the size. It's one possibility, right? Now, what happens if, let's say, the hair, and I'm not going to do the math now, but I just would like to illustrate it, show you anyway. What happens if the hair is kind of I don't know, diagonal, right? Like this one over here. Okay. Well, then you have to use Pythagoras a little bit. Right, I'm not going to do the math now, but because then you have to include the x and the y differences, right? Like in a triangle, right? Then you have to measure this here, the position here. You have to measure this distance, and then you also have to measure the distance down, and so on. And then you can, so you got to use a little bit of trigonometry to calculate it then. But if the object is horizontal or vertical, then it's quite easy to do. Okay, just wanted to show this to you, that this built-in stage, that essentially many microscopes with a mechanical stages is quite a nice possibility here. Okay. My suggestion is also, if you want to, we can have a look at a few cells, the plant cells. My suggestion is, if you would like to calculate, let's say the size of certain cells, that you actually measure out the diameter of, let's say, 10 cells and then divide it by 10. Because if you measure out multiple cells and divide it, then you're also reducing the error. You're also dividing the error by 10. Okay. Just to show this to you, what is this here? Up. This is the cross section of maize. It's way too bright. Okay, let's say 20 times. Yeah, let's focus a little bit. Yeah, same idea over here. Okay, look, the thing here is a little bit off, so much better. So let's try. This here is a so-called a vascular bundle. Basically, this is the xylem and phloem. I already talked about this before. This is where water and nutrients and minerals are transported up and down the plant. And those little structures, these are the individual cells. But I would like to now know, what is the diameter of such a vascular bundle, which contains maybe hundreds of cells, right? So I'm actually going to put the arrow on one side over here at the top. Okay, and I'm going to read off the value. And what is the value? The value is what? 15 point something. 15 point, where does it line up? 15 point, here it lines up. 15.7. Okay, 15.7 millimeters. So I'll write this down, 15.7 millimeters, 15.7 millimeters. And then I'm changing the position. Oh, no, wrong way. The other way, and other way like this here, where the arrow points now to the bottom side here. Like this arrow over here, right? Now on the bottom side. Ooh, I should not have moved the arrow, but I did not move it down. Okay, and now I have what? 15 point, approximately 15.5. Okay, so it's 15.5 millimeters. Again, it's 0.2 millimeters. So, oh, right, really? So this means basically the vascular bundle of corn, of maize, has approximately the same diameter as one of my hair. Okay, from 15.7 to 15.9 millimeters, your difference is 0.2 millimeters. Okay, so you see, this is a very nice and easy way to kind of estimate the diameter. I kind of like this system because it's so simple. But I would like to now show you another possibility. Okay, yeah, please do post comments and questions. Okay. Because what I would like to do is I would like to, even if they're not directly related to this topic, I'm going to later on, after I explain you the 3 methods, I'm going to then again go into the chat, and I'm going to then read down the chat, and I'm going to then answer the questions or comments that you might have. Okay, so possibility number 2. Okay, look, possibility number 2 does require a little bit of math. Okay, and I would like to show this to you as well. And what you need is a ruler, or rather 2 rulers. I've got let me show you over here. Okay, here we go. I've got a triangle. It's just a ruler, and here's a ruler as well. Okay, and what I'm going to do now is I'm going to use, because some of you have already seen in the comments that, well, those micrometer slides are so expensive. Yeah, I wouldn't say they're very expensive, but if you have a ruler like this, you can also do a little bit of experimentation. Yes, this ruler is not quite as precise as a micrometer slide, but it also works. It's a little bit of a proof of concept that I'm going to show you. We're going to use the ruler as a reference, even for higher magnifications. Yeah, you gotta bear with me now, okay? So what I'm gonna do first is I'm going to change all the way to the lowest magnification, okay? What I'm gonna do now is I'm going to put this back again. Just a second, can I put this back again to small, okay? Oh, no, here we go. And stage, I'm going to lock this again. I'm going to remove the arrows again, put them over here. I'm going to reduce the light, and I have now the 4 times objective in place. You know what? I'm going to change this now. I'm going to now show you the stage again, okay? Because I have to also turn on the lamp here's the lamp, and I have to focus my camera. Okay, and what I'm going to do now is the following. I know you're going to think I'm a little crazy, but I'm actually quite serious. I'm going to use now the ruler as a reference. Okay, to make sure that this is kind of straight. Okay, and I'm going to focus. Okay, so and now we need a little bit, a little bit of math here. Okay, so what I have is the following. I have over here millimeters, and I'm using now the low power 4 times objective. And I can see that I'm able, with a 4 times objective, I'm able to 1 millimeter, 2 millimeters, 3, 4, 5. So the field of view, at least with the cameras, around 5 millimeters in my case. It's probably going to be different with your system. Depends a little bit on the camera system that you have, and so on. But I now have a certain, I'm now able to measure out what 1 millimeter in real life on the ruler is on my screen. Okay. And then I can essentially, do a little bit of math, and then I can calculate the diameter of certain structures based from this reference here. So, and I would like to tell you another thing. I told you a few minutes ago that it's possible to also go up to higher magnifications. Look, 200 times still works. This is the 20 times objective that I have. But 40 times won't work because I'm zooming in too much and I'm not able to fit 1 millimeter on my screen or on the camera. But you don't need to, because what you can do is the following: is you can use now over here a ruler, another ruler, okay, and you can now measure out how many millimeters 1 millimeter in real life is on the screen. And this is with a 4 times objective, and with the 10 times objective, it's 2.5 times more than that. You can simply multiply. So, and with a 40 times objective, it's 40 times objective is 10 times more than the 4 times. You multiply it by 10. Yeah? So essentially what I have to do is I have to measure out on my computer screen by putting a ruler on my screen. I have to measure out now how big is the distance of this millimeter on my computer screen. Now, as you can see, the black lines of the ruler are a little bit thick. Okay, let me refocus a little bit. Okay, so where is the center here? So it's kind of, I have to now the 2 arrows over here. I have to kind of, where is the center? That's not a very easy way. We have to find the center. So what I suggest always is that you either use the left side, or in this case, let's say the right side. Okay, and I would like to measure out the distance between the right side of the black line and the other right side of and that's exactly 1 millimeter, and it's kind of easier for me to measure out because the contrast is much higher. Okay, so this is 1 millimeter and on screen. So I'm going to take my ruler now, and I'm going to go on the monitor, and I'm going to measure out how many millimeters it is on my monitor. It's going to be different in your case. Don't worry, this will be calculated away. And I have 50, how many millimeters? You mean, of course, you're not able to see this. I'm just holding the ruler to this computer screen. It's 50, 51, 51. It's a pretty, no, 50, it's actually pretty big of a coincidence. It's exactly 50 millimeters. That's a coincidence, okay? So I've got 50 millimeters on my computer screen is 1 millimeter in real life. Okay, so what I'm going to do now is I'm going to remember this, and I'm going to now go back here, and I'm going to now show you the math. It's actually direct proportion. Oh, I need to wipe this. Okay, so and it's really direct proportion, and I'm going to write this down, and I write down 1 millimeter in real life corresponds to 50 millimeters on the screen. Okay. So that's the reality, and that is the magnified image on screen monitor. Okay, so 1 millimeter in real life on the ruler corresponds to 50 millimeters on the monitor. And now what I would like to do now is I'm going to now go back to the specimen that I have here. Okay, and I would like to measure this out now. Okay, so let's put back in. So this here was, the 1 millimeter is 50 millimeters on the screen. I'm now going to take away the ruler, and I'm going to put in my slide again. Okay. And I'm going to again, focus this a little bit. Okay. And because the magnification is now 4 times, look, I would like to measure the diameter of one of those vascular bundles again. And remember, this was 0.2 millimeters before, right? Using the stage micrometer. And what I'm going to do now is I'm going to use the ruler again, and I'm going to measure the diameter on the screen of this vascular bundle. Okay, so let's try that. So I'm going to take again my ruler. Okay, it's I hold it on here on the, and it is of course what did you guess? 10 millimeters. 10, it's a centimeter. 10 millimeters. You just gotta believe me now, okay? So what I'm gonna do now is 10 millimeters. So let's have a look. Go back here. Okay, here it is. So X, I would like to know the real size. A corresponds to 10 millimeters on the monitor. Okay, it really doesn't matter whether you write the reality on the left side and the monitor size on the right side or vice versa, as long as, it's always on the same side. Okay, so this is the 50 millimeters is the monitor measurement and the 10 millimeters is the monitor measurements. And the units are all the same as well. And then we have to solve for X. How do you solve for X? You cross multiply this times this divided by this. Okay, so it's 1 millimeter times 10 millimeter divided by 50 millimeters. 1 times 1, okay, so the millimeters cancel out. So 1 times 10 is basically 10. 1 millimeters times 10 millimeters is 10 millimeters. Divided by 50, units cancelled, equals, what's 1 divided by 5? 10 divided by 50 is the same as 1 divided by 5 millimeters equals 0.2 millimeters. Same result. Okay, same result. Okay, so this is, I think this is just a simple cross multiplication we solved for X. Yeah, this times this divided by this. It doesn't matter if it's written left or right, as long as the monitor and the reality are properly aligned, and you get the same results. So the diameter of the vascular bundle again is 1/5 of a millimeter. It's 0.2 millimeters. Okay, so that is just kind of confirms a little bit the whole thing. Now you're gonna say, well, I don't know, I'm not so happy with this because it's the 4 times objective over here, but it's kind of too small. I would like to be a little bit more precise, and I would like to actually go up with the magnification here. Okay, and what I would like to do now is, no, not the 4 times. I would like to magnify the whole thing with a 40 times. Okay, I need more light, way more light. Okay, this is now the 40 times objective. Okay, here it is, the vascular bundle, right? Here it is again, right? How does this work? Okay, with the 40 times objective, it was that actually 1 millimeter was 50 millimeters in real life. So I'm going to show you now the whole thing again. Okay, so originally, let's do the following. Let's do the measurement first. Okay. Let's do the measurement first. I'm going to use my ruler again. I'm going to measure. It's a little bit diagonal now. Now I actually see that this is not a perfect circle, but it's a little bit stretched out. It's a little bit elliptical. Okay. So what I'm going to do is here. I'm going to maybe just measure the larger diameter over here across. Right. Maybe that's what I'm going to do. I'm going to measure out the larger one. So I'm going to hold the ruler against my monitor diagonally, and this is now what? It's 120 millimeters. Okay, so it's 120 millimeters. Let's remember this with a 40 times objective. Okay, so let's do the math again. 1 millimeter corresponds to, be careful, 50 times 10 now, because this is a 10, it's a 40 times objective is 10 times more than the 4 times objective. This was for the 4 times. Okay, and now I have to use the 40 times objective, so I have to multiply this by 10. Is 500 millimeters. This is of course way too large for me to measure out on the computer. My computer screen is not that large, right? Yeah. So I simply scale it up, okay, as X. And what did I say? 120 millimeters. Okay. This is what I just measured out here, right? This thing over here. Yeah, I measured out this distance over here. It was 112 centimeters. 120 millimeters. It's pretty large in my screen. It's 120. That's correct. Okay. Let's see if we're able to get a similar result now. Okay. So this times this divided by this. So 1 times 120 is 120 divided by 500. okay, equals 12 divided by 50. I got to use a calculator now. Does this work? Ooh, okay. My calculator died on me, so I'm going to use the computer calculator. It's what? 12 divided by 50, 0.24 millimeters. Okay. Yeah. It's a little bit more than what I got before, but this one is then 0.24 millimeters. So I just wanted to illustrate with this example, and I'm not going to leave the math. I just wanted to illustrate with you that you're also able to work with higher magnifications, because as I scaled up, went up with the magnification, I simply multiplied the measurement of the millimeters by how much more it is. Okay, so I made the measurement with a 4 times. I had no problem seeing 1 millimeter here, but then I did the microscopy with a 40 times objective. This is 10 times more, so I also have to increase this here by 10. Yeah. And that's it. Okay, so this basically shows that you can also make measurements using a ruler as a calibration tool, so to say. Okay, so that is was method number 2. Okay, I'm just checking the time now. How long have I already been talking? 35 minutes. Okay, please keep on posting questions. Okay, after the third method, I'm now going to show you the micrometer slide, and afterwards I'm going to call it quits just for this theory part, and I will be showing you some slides that we prepared last week, and I'll go through the chat. Okay, so I know that some people don't like math so much, but I kind of think it's good to know, okay? And if you're not so interested, then at least you know that these possibilities exist, and then later on you can always basically join in and watch the video again if you need this as a reference. Yeah. So possibility number 3, okay? So possibility number 3 is the following. Where did I put it? Is this one over here. I bought myself some time ago a micrometer slide. I think I bought it over Amazon or so. It's a calibration slide. And it's difficult. I'm going to use the white background maybe here. I don't know if you're able to see this. There's some text written on here. It says here in the corner calibration slide, and there are different types of divisions on here. And I'm just going to show this to you now, and I'm going to, let's have a look at this, okay? So I'm going to go back again to the microscope view, okay? And let's have a look here at the lone power again. Let's go down with the intensity. So, and let's put the calibration slide in. And let's have a look how this looks like. And it's a little bit, I have to find it now. Let's have a look here. It's upside down, of course. You know what? It says here calibration slide. Because of course images under the microscopes are always upside down. Let me flip it around so that we can read it better. Okay. So it says here, where is this? Yeah, it says here calibration slide. The text is of course way too small to be read. Okay, and this is a so-called a micrometer slide, calibration slide. Okay, and on here, and now this is a little bit difficult for me to find because I don't know where it is. Here. Yeah, let's see what it says here. Let's start on one end. Yeah, the diameter is 0.07 millimeters. The diameter of what? Apparently the diameter, of the diameter of this line. Okay, I just realized that my slide is kind of dirty, but I think that's okay. Yeah, so it's 0.07 millimeters, the diameter. Okay, so what else do we have? Let's go over here to the other. This one over here is something over here is the diameter is 0.15 millimeters here. What is that? See? It's already a little bit thicker. Let me remove the arrow over here. Okay, so you can actually, these, Then let's go again. What does this say here? Yeah, 1 one division is 0.01 millimeter, so 100th of a millimeter. Okay, let me move the arrow out of the way. Let's have a look here. Where are, look at this here. Yeah, and those divisions are so small that you cannot even see them yet. Okay, they're so close together, so I have to really, go in further. And I think there's also a last one. What does this say? Maybe one division is 0.1 millimeter. So that's half of the diameter of my hair and of the vascular bundle. So where is this? Yeah, here we go. Okay. Yeah. So one division is 0.1 millimeter. Okay, so from one line to the next line. Okay, so let's see how this actually works. And what I'm going to do now is I'm going to do the following. I'm going to put in the slide again, the other one with the vascular bundle of maize. Just a second. Okay, and yeah, I'm going to first remember the positions. Okay, I'm going to remember the positions, yeah, by marking, by placing two arrows, okay, on either side here. Okay. By placing, you know what, I might actually go up with the magnification a little bit. This is a little bit too difficult to see. Okay, so let's do this again here. Here and here. And it should be approximately 0.2 millimeters, okay? So this is basically, I'll remember this. And now I go over to the calibration slide. And now this is gonna be more difficult because it is at a higher magnification. So that's 0.01. That's not the one that I want. I want to have this is one division. That's huge, okay? Is 0.1 millimeter. So let's have a look. Okay, where is it? Yeah. Okay, here we go. Let's start here. Just for the fun of it, let's start at 0 because you always start at 0. Okay, so I have aligned now the left arrow with the 0. Okay, and the right arrow over here is at 0.1, 0.2, 0.525 maybe, right? This one here is right a little bit in the middle here. Wrong button again, wrong knob, not button, knob. Okay, it's a little bit more. Okay, 0, yeah, 0, so 0.2 maybe 6, yeah, 0.26 millimeters. Okay, so this is kind of the thing that I want to simply wanted to show you. I'm going to answer one of the questions here. How do you get these arrows to show in the monitor? I'm using the software called OBS Studio, which is a streaming software, which is a freeware. And I've made those arrows and I can superimpose them and I can move everything around. So basically, I've designed those arrows, so to say, and then whatever objects I place on top, I can move around. Yeah, just as a quick answer, I can duplicate the arrows and copy them and whatever, right? So just as a short answer here. Yeah. So you see, with the estimation I got with a slide scale, I got about 0.2 millimeters. And 0.2 millimeters now with a micrometer, depending also a little bit on the size of the vascular bundle, 0.25. Before that, I calculate 0.24. So you see that it's all pretty much in the similar size range. Okay, and what you can do now, of course, is you can use this information to take pictures and make scale bars. However, before I now talk a little bit about the comments in the chat, I want to say something concerning scale bars and magnification, because I get a lot of comments and emails from people who request that I put the magnification into my videos. I've got here's only one of my, one of the 2 microscopy channels that I have. In my main channel where I show you nature and where I put specimens under the microscope, many people understandably, I have to say, would like to see a magnification. However, there's a problem with that. Why I don't put it in there? Because it can be misleading. And when I say in the corner, the magnification is, let's say, 10 times, then what does this mean? It does not mean, it is misleading because there are 2 types of magnification. One of them is linear magnification, the other one we just call magnification. You see, when I put down 10 times, then what does this mean? It does not mean that the original specimen is 10 times smaller than what you're able to see on the screen. And different people who have a different monitor size will actually see a different magnification. But what the people actually want to know is what objective did I use? Someone said, okay, I used the 10 times objective. Then I have to specify, I used the 10 times objective. But if I use the 10 times objective to show you specimens and you use the 10 times objective, then it does not mean that you see the same thing, because what you actually see is only a small section of the field of view depending on the size of the camera sensor. You see, it's becoming complicated very quickly, and for this reason, it's I don't always find it very meaningful. So the only thing that would be meaningful would be to include a scale bar in the corner of the videos. But I have to be honest with you, I sometimes zoom in and I rescale the videos just to make sure that the specimen that I show you kind of fills the whole screen. And then the scale bar, also has to be scaled appropriately. And this kind of makes it a little complicated. And for this reason, I do not include a magnification, right? So I just wanted to clarify this a little bit with you, or kind of explain to you why I do not include magnifications in the videos, okay? I just see in the comments here, camera resolution, sensor size, and all of these things have an influence, and therefore it cannot be easily compared, right? In any case, and sometimes it really doesn't tell you a lot. If I give you a scale bar and I say it is 225 micrometers, what does this tell you, right? If there is no real life connection, it's kind of difficult. It's correct. The scale bar has to be placed in the image before zooming. If you actually do zoom, then the scale bar will zoom accordingly, and therefore it will stay correct. But that's the thing is with videos, it's a little more difficult because sometimes I want to zoom in a region where there is no scale bar. Okay, just saying that I've encountered some practical issues here. People, you know what? This is actually all I wanted. I talked 46 minutes already about a theory, and I'm going to now do the following. I'm going to interrupt myself now with the scale bar and with all of the magnification calculations, and I would like to now dedicate the remaining time to answering your questions. Okay? We're going to see how this actually works, and I would like to start off. Before I do that, just give me maybe a couple of minutes. I just want to have a look at the specimens first that I prepared last week. And if you joined my live stream last week, I put some mites, some varroa mites, which are parasites of bees. I mounted them in U-Pearl mounting medium. And I would like to look at them again and see how they're doing. Okay, so I have to remove the slide here, and then I'm going to go through, as promised, the chat to answer some of your questions and comments and whatever. Okay, so let's have a look here. Always start off with the lower magnifications, of course. I don't know how this guy is doing here. Okay, let me see. Here we go. I think if you joined me last week, maybe you remember that I told you that U-Pearl has the tendency to clear insects, and these mites are not insects, I know, but insects and spiders and arthropods in general, okay? And you can see that, as a matter of fact, it is much brighter, but there is a dark region in the inside. And this dark region, especially here on the side, there's this dark. This is somehow an indicator that there might be some air trapped in here, okay? And because there is a huge refractive index difference between the mounting medium and air, that's why sometimes where there are air bubbles or so, or trapped air there, you see that the corners are kind of darker, okay? Just saying, but I think if you remember last week's yeah, how the specimen looked last week was almost completely black. Okay, so the the UPROL did clear quite a bit, but that's not the only thing I want to show you. And the mounting medium is probably also not completely dry yet anyway. Usually, as I told you already last week, it usually takes around a month or maybe 6 weeks, depending a little bit also on the temperature. Okay, so where is this here? Because I cannot look through the micro. Here it is. Yep, here another one. I think it's becoming quite clear. it's quite clear that the specimen has cleared. What a pun. Okay. Again, over here, this seems to be an air bubble, and everywhere there are air bubbles, there are some issues. Okay, with clarity. Yeah. But I think I think I kind of demonstrated this way that UPROL now you know why UPROL is so popular with folks who are studying spiders, insects, arthropods in general, because of this clearing effect. Okay, so let's have a look at another one, another mite. If you have not been here, if you don't know what I'm talking about, because you have not joined last week's live stream is of course available. Okay. Where I mounted them. So here's another one. What's this? Ah, this was the stinger, right? There's not so much difference here. But again here, look, again here, this seems to be an air bubble which is trapped inside. Okay. So yeah. So maybe it does. I don't know. Again, I think I mentioned this before. Maybe one way of dealing with that is while the mounting medium is still liquid, kind of to expose it to a vacuum, because this will cause the air bubbles to kind of bubble out. And so this is the stinger of a bee. What is this here? This, I think, was this a bee's leg? A very, very thick specimen. So I don't know if this actually worked well or not. Yeah. Because that's maybe a little bit it cleared. I don't know. It's still quite dark. Yeah, still quite dark. It could be that if you, what I read, and I have to see this one, the clearing effect did not quite work quite well here. Maybe because the specimen is indeed too thick. Maybe it does need more time. I don't know. But what I read is that what folks have been using for clearing the exoskeleton before mounting it is a potassium hydroxide solution, KOH, and or a lactate or lactic acid. Apparently, both of these work to clear the exoskeleton and to kind of bleach it. Bleaching would also be an interesting thing. And that's the wing of the bee, which was already pretty bright last week, but it seems to have become even brighter. By the way, I'm now looking completely at bright field. I switched off my DIC. Okay. So that's actually the way that you should also be able to see it. Yeah. Okay. There's a comment now, a vacuum could cause the specimens to explode. Well, unless, could be, of course, but here we're talking about insects and spiders and arachnids who have a very, if there's a little hole in the exoskeleton somewhere, then I think this will allow the air to escape and it will not pop open. At least I hope so. Okay. And let's see. So these were all UPROL mounted. Now that's the next thing is, I don't know. The next one is now PVA glue. Now that would be interesting to see if there was also a clearing effect in PVA glue. I gotta find it first. I'm gonna go down with the magnification first. Here, where was it? That is PVA glue. The Elmer's glue that I've been recommending. Look, looks as dark as last week. I think that's a nice comparison. Okay. Again, on the side here, it's still a little bit brighter, but it's pretty dark still on the inside. I wonder if this is again because of some air bubbles. Yeah. There you see an air bubble over here. Yeah. Just notice that the 3 arrows are still there. That is correct. Now one of them, I'm going to make the arrows disappear. Okay, now there's only 1 arrow left. Okay. Yes, thank you for reminding me. I can switch on and off the graphics. Yeah. So for example, what I can do is I can also switch off the stage like this and I can turn it on. Okay. I can even switch myself off and myself on again. Okay, where am I? Here am I. Okay, yeah. So, and then I also tried, this was the recommendation or by one of my viewers, to add a little bit of detergent soap to the PVA glue. Okay, and let's see how this worked. Oh, there's a little, wow, look at this. Part of the specimen broke off here. It's almost fractured. I wonder if this is because of the tension in the glue as it dries. Yeah. Yeah, but still this one is quite dark. Yeah. So, yeah. So in this case at least, and there is still a lot of darkness in the inside here, so maybe still some air bubbles. So yeah, at least in my case, the soap did not act very much as a preventer of bubbles. Okay. Yeah. Okay. Just to wrap up last week's slides a little bit. So now I'm gonna start at the beginning. Okay. What time is it? Almost 1 hour. Wow. Okay. I'm gonna go all the way to the beginning. Okay, and now we're going to start. I'm going to start talking a little bit about the live chat. So again, hello from Costa Rica. Hi from Lebanon. Hello from Vienna. I have a question. When making a permanent mount with a small insect like an ant, should I first dry it or put it in alcohol, or does it depend on the mounting medium, PVC glue? First of all, if you dry it, it might shrink, or at least the organs might shrink. And if you put it into alcohol, the same thing will happen. The point of putting it into alcohol is to dehydrate it. And sometimes what has been recommended is that you do not put it directly into concentrated alcohol, but that you gradually increase the alcohol concentration to gradually dehydrate it. I think that alcohol treatment has maybe the advantage that it kills off bacteria and therefore preserves the specimen better because there's less decomposition happening. But then again, if you put it into PVA glue, it's going to dry up anyway, and then it's not going to make a huge difference here. Okay. Generally, I think that it depends a lot on the specimen, and you have to try it out. What is the best thing to do? Okay. Because I think they changed after some time, and that was due to the trapped moisture or something similar. I get it. Yes, this could be possible, but then again, there is in the PVA glue, which is water-based, there is a lot of moisture anyway. Okay, and I think you mentioned mount a fresh silverfish in U-Pearl. I don't remember if it turned out right. However, U-Pearl containing it's kind of cruel anyway to mount insects like this, but U-Pearl contains a solvent, right? Yeah, and this also has automatically some kind of preserving activity because it kind of disinfects as well and removes bacteria. Okay. Hello from Stockholm, New Jersey, USA. Stockholm, New Jersey. This is Stockholm, New Jersey, from Cologne, Germany, from Vietnam again. Again, yeah, 3:30 in the morning somewhere. Greetings from the Netherlands. I have some exciting news. I wonder what it is. Okay. Seratin, 30 miles east of Hamburg. Okay. Yeah. Somebody's celebrating birthday. Happy birthday, of course. Okay. Greetings from India. Happy birthday. Yes, lots of greetings. Okay, sound is good. I'm gonna jump ahead. Don't feel bad if I don't mention you. Okay, micrometer slides are so expensive. Well, I wouldn't say that they're necessarily always cheap, but actually mine wasn't that expensive. Okay, yeah. So yeah, so. You know, I will put my, okay, happy birthday again. I'm just trying to find some microscopy related questions. I remember you saying in a review video of my microscope, which is SW380T, I think, and you said that the scale was inverted. Would it change the calculations? Not at all. I remember that there was, there was once I made a review video and I've seen that the scale seemed to be inverted. It's a little bit a question of taste. It depends how you rotate the head of the microscope. And some people like it in one way, some people like it in the other way. But I would have preferred it to be the other way around. It doesn't matter. It makes no difference at all to the calculations. Really, okay? Micrometer slides aren't expensive at all. They're like $15 or 15 euros. The fancy ones are more expensive, like $45, but it's not expensive compared to other microscope stuff. Yes. I've also bought once a so-called a hemocytometer, which is a special type of slide which allows you to calculate blood cells. I might be also doing a video on this, just yeah, for teaching purposes. And these slides are indeed a little bit more expensive. Not also, yeah, I think I paid around 40 euros for one of them. Okay. You should buy micros. Hello from Massachusetts. So it's basically small. Yeah. Yes. It's a small caliper. That's correct. Yes. Off topic, I have a Carl Zeiss inverted scope. I have numerous objectives and eyepieces. I cannot even get close to a focused image. Everything works. Inverted microscope. Well, I'd have to look at this. Honestly, I don't know about this. If it's blurry or not. Maybe there's some other adjustments. Maybe the condenser might be off a little bit. Yeah, you'd have to check that. So there are several things, if you don't get a clear image, several things that have to be checked. Okay, my local retailers are trying to hog them for 90 euros. I'll look elsewhere. 90 euros is kind of expensive, I would say. Okay, but I cannot deny it. Maybe there are some special purpose calibration slides. Yeah? On Amazon or eBay, you can get them for a reasonable price. Yeah, about $15 at Amazon's. Yeah. No, it's so interesting. I wonder what is the math behind this topic. Yeah, the math is direct proportions. I mean, when I was at university, I did had to do calculations every day, and direct proportions are the most common things. I don't know, I had to mix chemicals, and how many grams of a certain substance do I need to get the same concentration. So direct proportion calculations were something that I had to do every day. Yeah, so, and that's I think was very useful. Hello to Oliver and everyone else. Yes, microscopy. That's brilliant, because it's actually size and movement of the stage is constant, so the measurements are constant too. Yeah, of course. The magnification only increases precision. That's correct. The higher you magnify, because the thing is the following: the measurement area that you make, okay, is always the same. But if you kind of make it bigger, then the size of the object is much larger than the error that you make. Okay, so that's kind of the idea. And if you, for example, count, I don't know, 10 cells, the diameter of 10 cells, and then you divide it by 10, then you're also dividing the measurement error by 10. That's the reason why you want to make larger measurements and then kind of divide it down, because this way you're also reducing the overall error. Okay. Bye, Tinian again. Say if I'm okay. Happy birthday. Yes, it's interesting. You're okay. Hello. I'm doing a little bit later. Did you read my big news in the live chat? Yes, I read the news. Happy birthday. Okay, happy birthday, everyone. I don't know you remember what microscope you were using. Never mind. Thank you. So there's a lot of chat going on between members of the community, which is perfectly fine. And I like that when people essentially start to talk a little bit to each other. Okay. But there are not so many questions right now. I wish I knew how they made the slide for the cross-section of maize. Maize is corn, right? And that's the slide that actually my desktop background looks a little bit boring. Why not show you this here again? Okay. What they have done is they have used a microtome to do that. Okay. A microtome is a little device that allows you to make very thin cuts. And these slides are made professionally by a company who are selling those slides for educational purposes. Okay, and what you're able to notice is that essentially it's only one cell layer thick. And by the way, one aspect that I did not explain yet, I'm going back to the measurement. Okay, I'm going to move this now over here. Do you see the scale over here on the fine focus? Okay. These are also micrometers. Okay, so you can also measure thickness this way. Maybe the topic of another video, of a live stream. Yeah? But the scale on the fine focus also has a meaning, right? So that's basically a maze, and this has been made by using a microtome. A microtome is a device that makes very thin cuts, and if you do check some other videos of this channel, then I've also introduced and showed you some different types of microtomes. And there was actually also one video a couple of years ago where I actually also showed you how you can make your own microtome like this. It's an improvised one. There's a little screw here. You know what? Now I'm going to switch back to the desk view. Okay. This is the spool of some string, a plastic spool. There is you can see over. I mean, it's pretty self-explanatory. And what you do is you put the object, the stem, for example, in here, and then I don't even have a knife with me. let the ruler be my knife, and then you kind of cut it across like this. You rotate to push it out a little bit, and then you cut again. Okay, so this is a highly improvised one, and you know what? It actually does work. Okay, not as good as some commercial ones, but it is indeed a help to make thin sections. Yeah, you just have to make sure that when you cut it, it stays in and does not lift it out. Okay, so I gotta see where I am. Yeah, my microscope has 10 as top value. Just make sure, would this change any? No. Look, the thing over here. Let me go back over here. Yeah, over here, where does it show? This one always goes from 0 to 10, the small one, and the other one over here can have can be however long it's necessary. Okay. Yeah, that's just the whole movement of the stage. In my case, the stage moves and the small one stays the same. In some other microscopes, they're different possibilities. And this one over here is the other one. Yeah, it's behind it. Yeah, so because you're calculating differences anyway, right? You have the starting position and you move it, and you have the end position and you calculate the difference. Yeah, so as long as you're able to read off both values, it doesn't really matter. Huh? Is it possible to calculate the length using a computer system or program? Yes, as a matter of fact, and indeed there are programs that do that. Specific programs who are also able to measure out certain distances, also diagonal distances where you have to use some trigonometry. Yeah, this is indeed possible, and there are programs that do that. Okay, and also there are even statistical methods. I've got a book. I gotta check up on that. How you can, if you have some kind of a fiber that is bent, okay, kind of squiggly, okay, there is even a statistical way to estimate the length of non-straight lines. You somehow have how often it crosses a reference line. You can, and if you can average it out, and you can estimate the length even of irregularly shaped lines. So that is possible. Oliver, do you already hear about the fluorescence glow scope or simple smartphone microscope that you can build for less than? No. Well, I know that there are some 3D printed microscopes out there that I started to experiment around with, but simply the 3D printing time took me so long, so did not get around it yet. Fluorescent microscopy can be done by using ultraviolet light LEDs. And I already said that I'm experimenting also with some LED flashlights, and you can do something called autofluorescence. And autofluorescence means that the objects, they start to glow on their own. You don't need any special stains. Why do so many people have a fear of maths? There is I've read somewhere that this is a book I read once, and in the introduction it said it was actually about math. It was about cryptography, totally different topic. But it basically they said it was in the introduction. It says the publisher said it's every formula that you include in the book will reduce the number of readers by 50%. For whatever reason, right? I don't know why people have a fear of math, but unfortunately, yeah. Because 7, that's a pun. 7, 8, 9, yeah. Off topic, is there a difference to qualify if I stick a microscope camera in a trinocular third hole or in a binocular ocular? Is there a difference to quality if I stick a microscope camera to a trinocular third? Okay, no, there should not. So the question is if you put a camera, you can either put a camera onto the follow tube, or you can put a camera into the eyepiece. Let's say that you remove the eyepiece and you put in the camera directly, and no, there is no difference in quality. Okay, because what happens is that the image, it's called a beam splitter, is simply redirected either through the eyepieces or out the follow tube, or both. Okay, so there should not be a difference in quality. However, the reason why you have a follow tube is primarily for two reasons. First of all, you can mount also heavy cameras like DSLR cameras without the danger of the microscope tipping over. Okay, the second thing is simply convenience, because you would like to look through the microscope And then if you see something, you can take a picture with a camera on top, and you don't have either or, right? You can do both at the same time. So it's convenience. And if you have a heavy camera on your eyepiece, it's also possible to do that, but then you should support it somehow with a tripod. Otherwise, the heavy DSLR camera, if you use a heavy DSLR camera, it will kind of push down a little bit too much. But those eyepiece cameras, they are so light, you just plug them in and that's fine. So it's mostly a question of convenience, but not quality. Very similar to scale on setting circles of telescope mount. Yes, great for finding faint objects. Of course, most new telescopes are computerized. Yeah. Okay. So 10 divided by 50 is 0.2. 10 divided by 50 is basically 1 divided by 5. It's 1/5. 1/5 is 0.2. Correct. Okay. Hello from Greece, Mr. Microbehunter. How do you mark where the depth is on the microscope? You can't zoom or adjust too much focus or the ratio is lost. I have a problem understanding this question. Sorry. The depth is on the microscope. You can't zoom or adjust too much focus or the ratio is lost. Is it like this, that you're kind of, if you're focusing, well, focusing is not zooming. Okay. So yeah, I mean, I know with stereo microscopes, it's an issue, because with stereo microscopes, when you kind of go down a little bit or up or down, then those parts that are closer to the lens appear larger. But I'm not quite sure if I follow your question. Yeah. I know you don't recommend 100 times oil immersion objectives for novices, but I've seen 100 times dry objectives. What is your opinion of those? I know that there are 100 times dry objectives, and there are also 100 times objectives that can be used with water instead of oil. The idea is the following. If you use dry objectives, you cannot have the same resolution. Okay, that is really the point. That means you don't get the clarity. So you might as well use a lower magnification objective. But then again, my suggestion is this is a hobby. Okay, we want to have fun. We want to learn something. Try it out. Yeah. The reason why I don't like to use oil immersion is because it's messy, and because I'm kind of afraid of ruining my other objectives. Because you see, I'm mindless, and then I rotate my 60 times objective, which has a very small working distance, into the immersion oil, and then I have to clean that, and I don't want to do that. And you see, those objectives are not designed with immersion oil, and then it can be that immersion oil goes into the objective, kind of pushes next to the lens, and then I have to send in the objective to get it cleaned, because I cannot do that, right? My objectives are better objectives, so they can be actually disassembled and they can be cleaned, but I have to send it into the company. I don't want to do that. So for this reason, I'm really careful, and I try to avoid oil immersion as much as I can. Okay, and because there are some cases where you have to use it, especially if the specimens that you want to look at require very high magnification. But for most hobby purposes and amateur purposes, I don't recommend them. And also, if you have permanently mounted slides, you don't want to use oil immersion on them anyway. Because otherwise the oil is everywhere and messes up everything, right? My recommendation to microscope companies is don't supply an oil immersion, 100 times oil immersion, but a 60 times dry objective. This would be my recommendation, because there is still a slightly larger distance. This means you can also look at slightly larger thicker specimens without crashing the objective into the slide. I think it simply has more, more applications. Right. Having said that, there were a couple of algae that I really liked to see under oil immersion, because they were kind of small, and I got a really nice image with oil immersion as well. Okay. I did not know about the 12 objectives, neither did I. But again, they don't have the numerical aperture and the resolution. They cannot have that. But and then maybe you just might be as well off with a lower magnification objective that has a similar numerical aperture. The numerical aperture is the value that's printed on the objective, which tells you something about the resolution that the objective is able to provide. Okay, how do you get these arrows? Yeah, as I just mentioned, I'm using OBS Studio, and I can essentially include any graphics and overlay any kind of graphics that I want to use. Okay, yeah, okay. I think most applications for microscope cameras have the possibility to draw arrows, lines, and dots, which could be easy for taking measurements than using mouse pointers. Yes, that is correct. And the reason why I used this mouse pointer, it is actually not a real mouse pointer. It's simply a graphic that I superimposed. Okay, so it's not which kind of looks like a little bit like a mouse pointer. I made it also semi-transparent, but it is correct that there are software. One of the software that which you can download even if you don't have the camera is ToupView, T-O-U-P View, which is a common software for microscope cameras. And even if you don't have a microscope camera, you can experiment around with it, and you can simply open pictures and you can make measurements with that. Okay. That's a good point. Also, also the camera resolution and sensor size. Yes, the scale bar has to be placed in the image before zooming. Yes, that's correct. I talked about this. You can also use an eyepiece graticle in combination with a micrometer slide. After calibrating, you can directly view the size. What is possible, and I also made a few years ago a video of this, and in this very same channel, what I've done is I actually printed a scale on an overhead foil, and then cut it out and then put it into the eyepiece. Okay. That's possible, and when you look through it, then you're able to see the scale superimposed on the image. Yeah, so I made some time ago, I made a video of this. You might be able to find it somewhere if you go back in time a little bit in this channel. Yeah, so I've been playing around with that as well. Yeah. Hi, will you show the calibration and use of the micrometer eyepiece? Okay, I don't have a. Right now in my microscope, I don't have a micrometer eyepiece, but I can try to get one. But then, yeah, I'll think about this, yeah? The clearing effect has worked. This refers to the slides which I made last week, okay? And one thing I've been thinking of trying is stacking the specimen slide on top of the micrometer slide. That is interesting, but this might be difficult to do. You know, but why not? That's an interesting point. With a low power, it should work. Look, let me try. Let me try. That's something I've never tried before. So actually, thank you for the recommendation. So what I have to do now is the following. We gotta be a little bit. The thing is, the print of the slide of the micrometer slide is on top. So if I now basically put it. You have to make sure that the specimen and the slide are close together. So I might have to turn it around. You see, it's now on top, and now either one or the other is in focus. Okay. So either one or the other is in focus. So especially for the higher power. Yeah. See, but maybe, you see, but you know what? Yeah, so this is basically when they're now stacked on top of each other. But you know what? What happens if I turn the micrometer slide around so that it is the print of the slide is closer to the specimen? Let me try that. But then, of course, there's a lot of glass between, so this might only work for the low power. Let me see if this actually. Now I have to find it. That's always a difficulty. Is always can I find it? Let me see. So that's now where can I find it? You know what? I'm still going to go down with the power. I have to. Here's something. Here it is again. It's too bright. Yep, it works better. It works better. Oh, cool. I've never tried this. You see now the focus is not so off. Okay. Because the print is now turned towards the specimen. Okay, and this way you're also able to. How big is where is this? It doesn't. I don't know where it says how much it is. You see, one division should be. I don't know where it is. Yeah. Here it is. One division is 0.01 millimeter. 10 microns. 10 microns is approximately the size of a red blood cell. 0.8 microns approximately. Okay. Yeah, but you know, the worry that I have right now is if I go up with the magnification yet further, I might crash into it because there is the 6 slide. No, it works. With the 20 times, it still works. Okay. So, yeah. So it is somewhat possible. It's actually, thank you for the recommendation. Okay, I've not tried this one. Okay. You can use an eyepiece reticle for this, then you can see the specimen. Yes, good to know. Just notice the 3 errors are still there. Would the creature decay after being put in Uparol? If you put a specimen in Uparol, what's going to happen is because Uparol contains a solvent, an organic solvent. Yeah, you can also dilute Uparol a little bit with alcohol, and this solvent will actually kill off many bacteria. Okay, provided that the Uparol solvent is able to reach all parts of the insect, of the creature. Because this is not always guaranteed. Generally, what you do is, if you want to really make sure that a specimen does not start decomposing, is you have to put it into an alcohol series to fix the specimen. This kind of stabilizes it chemically, removes bacteria, and then you can remove the remaining water in alcohol, and then you can mount it. Yeah, so it is indeed decaying is indeed a problem. Especially if there is still some moisture in there, okay, because this causes bacteria to decompose it, and then you have the problem that there are decomposition gases forming, and then you've got bubbles forming, right? The x-axis scale on my stage is very difficult to read because it's obscured by the objective lenses. Yes, I understand. This is the case with many microscopes, that the x-axis scale is kind of all the way on the back side and difficult to read. And I've seen some microscopes where the print of the scale is very difficult to read. It's black on black. So it's difficult to read there as well because they forgot to paint it. Yeah? Do you ever use Z-stacks for images? Yes, occasionally I do that. It's image stacking I do occasionally, okay? I'm super new in microscopy, and I have a very basic question. Everything we put between subject and the lens affects the capture quality. So basically, everything, I think the question is everything that you put between the specimen and the lens will influence the image quality, and this is correct. The cover glass, for example. However, and that's also important, the cover glass, the thickness of the cover glass influences this, but this is compensated by the optics of the microscope. So many microscopes will have a number printed on it called 0.17. That's the thickness of the cover glass, and this is kind of how the objective kind of compensates for that. Okay, so yeah. However, the cover glass does have the advantage that it makes sure that the specimen is very flat. Otherwise, it's difficult to focus. Is it really needed to use these small glass squares on the top of slides, especially like I plan to watch, let's say, onion skin? I will tell you the following. No, there are 2 cases that I can simply tell you off my cuff where you do not need a cover glass, but I still would recommend it to protect the objectives from the water. Okay. Case number 1, when you're using a low power, the low power 4 times objective. Okay. Why is no cover glass needed? Because the cover glass thickness will not have an effect on image quality. Okay. For the higher powers, you need one because the objective expects a cover glass, so to say. For resolution purposes. Here, there is also not so much danger because of the large distance that the objective will contact the thing. So it's kind of safe, right? And whether or not you use a cover glass will not make a difference to the image quality. And the second case where you do not need a cover glass is when you observe bacteria that are heat fixed and stained using oil immersion. I've not shown this to you yet, but with oil immersion microscopy, what you do is you want to observe bacteria. You often do not use a cover glass. You make sure that the bacteria are on the microscope slide. They're glued to the microscope slide because of heat fixing means you take the bacterial slide and you pull it through a hot gas flame, and this basically bakes the cells to the glass surface, and then you can put directly immersion oil on the microscope slide. Okay, so there is no cover glass in there. Yeah? And then you rotate the oil immersion objective into the immersion oil. Yeah? So there is basically the glass slide, bacteria on top, immersion oil, and then objective. Right. So these are the two cases where you don't need a cover glass. If you want to watch onion skin, honestly, you want to go up with the magnification anyway. And sometimes the onion skin is not always flat, number one. And number two, if you don't have a cover glass without water, then there is the problem that the specimen might dry out very quickly. Okay. And if you've got water directly on the specimen and no cover glass, then the water surface tension is going to form a lens, right? And you don't want that. It's got to be flat. And that's why you use a cover glass. So my suggestion, just use a cover glass, okay? But at the same time, for very quick checks at low magnification, I also don't use a cover glass. Just put the drop of water on there. Just to check if there's anything in there, right? Yeah, and I'm only going to use the low power. Put a small drop on here. I don't bother to put a cover glass, and put it on the low power 4 times, and I see, there's something there. Fine, I'll be great. Yeah, and then I continue observing. Yeah, so yes, I often go without the cover slip when I'm just checking to see if my sample has anything interesting. I just said that. Cool. I didn't read this before. Yeah, that's what I also do, right? If you use higher magnification objectives, it has to be really close to the slide, and you risk dipping the objective in the water. Exactly, fully confirmed. Yeah, I think glass covers can give a thin film, correct, to the sample, which could make the sample look better, correct. Since it squashes the samples a bit, it also limits vertical movement of water microorganisms. So they are in one plane and therefore much easier to focus. So if I want to magnify the hair, would it be better to do it with or without cover glass? Definitely with cover glass. Why? Because the hair otherwise will start to be blown away by the wind or your breathing. And you put some hair on it, you put a drop of water on it, cover glass on it, and the surface tension of the water will stick the hair between slide and cover glass. Everything's nice and flat. Otherwise, if the hair goes up or is bent, you basically, have to keep on refocusing, and you will not get a longer section of hair in focus. So cover glass definitely recommended. Okay. When you watch a dry subject, do you need to put some water on it to see it? Generally, if you put water on it, then it will become better visible. Because, for example, it depends a little bit on the subject, but let's say pollen grains or spores. Of course, you can put them under the microscope in air, but sometimes they will look much darker. And as soon as you put water on it, they will start to look much brighter. And the reason is because there's less difference of refractive index between the specimen, the pollen, and the surrounding water. So light is not diffracted as much, and this causes the pollen to appear brighter. That's simply the way that optics work. But I would say that it's always best to try out these things yourself, okay? Because then you actually see the difference with your own eyes, and then you're going to see that in most cases, I think it's better to put water on here. My Multicam has software that measures the diameter circumference. Yes, yep. There are often is software supplied. Tini is right about that. So if you have a lot of dirt, debris, and the droplet, it will spread it out. For here, it's not really necessary, okay? I love math. Yes, the glow scope. There is a Creative Commons open article in Nature. In the supplementary material is complete part list. Okay, thank you very much. That's this homemade fluorescent microscope. Okay. Now I lost it where I got lost. Oh, could you demonstrate how to see dust mites under the microscope, or your microscope not powerful? Oh, my microscope is very powerful, and dust mites are pretty big, as a matter of fact. But I have to be very honest, I haven't found any yet, so I gotta go out search for some. Okay, but it's not so much a question of power. Most pretty much all microscopes, or most of them, magnify already way more than you need. So it is, and dust mites are fairly large anyway. Would there be a difference in thickness of hair of humans and other animals? Sure, why not? Okay, other mammals. Not only that, but even human hair has different thickness, right? But why not show you? I mean, I made this hair sample some time ago, and let's remove this here again. You're going to see that even my hair from my head is not always the same thickness. Yeah. These are it's pretty dark hair still, but slowly my hair is also becoming a little bit white. Yeah, but if you look at this, even here, my own hair does not always have the same thickness. Yeah. So as a matter of fact, the eyelashes are quite interesting as well, because they are very pointed. Yeah? And people have been using their own eyelashes, because they're so thin and pointed, have been using their own eyelashes to actually manipulate some microscopic specimens under the microscope. Yeah? Why do objectives go up to 100 times, or is it possible to go 200 times or more? Look, if you could theoretically make pretty much anything that you want to make, but the problem is that any magnification that's higher will result in a blurry image. You will not gain more information. The image will become darker, because you're looking at a smaller space, a smaller area, and there is, of course, then the light is going to be spread out more, so there is simply less light there. It's going to be darker. It's going to be also significantly more blurry, because we've already reached the limit of physics of what light is possible. It's not a problem of making lenses that magnify more. It's simply we've reached the physical limit of light. Okay, and if you want to get a higher magnification, then you need to switch over to electron microscopes, because electrons have a much shorter wavelength and are able to resolve images or specimens that have a much finer detail. But with light microscopes, we are limited already by the physics of light. Okay, and we have reached this limit already, I don't know, 100 years ago or so. In optics. So it's not a question of microscope quality. Yeah, because it's simply we've reached the limits of physics. Okay, use the numbers on your stage dials. They are there for measurement. Yes. Okay. So let me quickly. Would it be possible to create a micrometer cover slips? That's an interesting one. It's an interesting one. I never thought about this. Why not? One thing that I have not tried out yet is maybe it is possible to use a laser printer to print, but this depends on the laser printer, but maybe you can print out some lines using a laser printer on overhead foil, and then kind of use the overhead foil maybe as a cover slip replacement. It's not ideal because of the wrong refractive index and because it's not completely flat, but maybe for experimental purposes, this would be kind of interesting to use. Okay, that you print your own cover slips on overhead foil, maybe with some kind of a scale. Just invented that possibility, never tried it. What about PVC glue mixed with alcohol? I don't know about that. Okay, don't know so much about about that. So let me see let's move on to the next. Could you do a lesson on focus stacking in the future? I could, and I see why not, but I already also made some videos about this. Okay, so if you are interested in focus stacking very quickly, then my suggestion is that you check out some of my videos. The live stream is 80 minutes long now. Yes, I know. And I'm starting to feel slowly a little bit tired. And I'm sure that some of you feel tired as well. So I'm going to quickly try to finish the remaining questions here. Okay. It's been quite a while since you made a water microorganism live stream. How are your ponds? Spring is starting to come slowly. So I think I might be doing some water sample collection again. Okay. Very much off topic, but great news. I'm going to get my Apple Plan lens for photography. Yes, I hope it's worth it. Okay, wish you all the best with it. Yeah, Congratulations, it's almost like my birthday. I come after hard work only to tell it's your fault I buy a microscope. Yep, I hope so. You showed a recent video of moving sand particles. Yes. Were you using a stereo microscope? No. Okay, that's actually in my other channel. The video I uploaded a few days ago is about sand particles that I got from Germany 7 months ago, and it was salt water, so the specimen still stayed fine. And I basically I just used a regular a combination of bright field microscopy and DIC, but you should be able to see it in the same way. Yeah, I did not use stereo, but I could have. Okay, so it would have worked as well. Okay, I use 160 for blood. Yeah, you are interested in photography. I don't know who you're asking the question to, but I at least am interested. Okay. Does the depth of field depend on the microscope objective quality price, or is it a pure physics and all objectives, no matter what price, exactly the same depth of field? The depth of field depends on the numerical aperture and basically also on the condenser setting. So no, there is no, to my knowledge, there is no depth of field issue here. It depends on the opening, of the aperture. Okay, and let's move on. So basically, the quality of microscope objectives are determined by the number of aberrations that are corrected, basically chromatic aberrations, and some of those objectives can be very expensive. Apochromatic objectives can cost, I don't know, a fortune, right? But they give you a very sharp image, provided that the specimen is properly prepared. Okay, sometimes if the specimen is properly prepared, then you won't gain a lot of benefit here. Or if the objective is a little bit dirty, you've lost everything again. So I quickly want to finish now. Brilliant work, thank you so much, much appreciated. A confused novice. I put a piece of crushed candy cane under the microscope. It looks like crystal. Add a little bit of water and you're going to see the crystals dissolve. Yeah, it is crystal because it is crystallized sugar. Yeah, and sugar is made of crystals. Add a little bit of water and then you can see the crystals dissolve. And ladies and gentlemen, over 1.5 hours. And I think we're all tired. At least I am tired a little bit of talking so much, but it was for me it was a great experience again. I hope also for you. I hope that you kind of liked it as well. The format is a little bit different. I did all of the comments very quickly now at the end. Okay, and I did the theory part as one block in the beginning, so that some of you who basically just were interested more in the theory part at the beginning then had the option to kind of cut it short a little bit. So maybe we're going to keep it like this also in the future, so that some of you who would like to join a little bit shorter can basically then opt out for the second part. Okay, I wish all of you all the best. Happy microbe hunting as always. Hope to see you again next week. And enough for today. Bye bye. Enjoy microscopy, and until next time. Bye bye.